Hi there. Welcome to More Physics. I'm going to make two, three, maybe three more videos to cover the rest of the material in the course, and hopefully, as I said at the end of the last video, hopefully but over these two, three videos, um, which should be online before the weekend, that will finish the module for you. Now, um, so what I'm going to do is just show you the where we are in the booklet. Um, Share. And we're now up to the cover the material that was formed part of what the experiment was in week 11. So measuring the resistivity of a metal. We've been through this theory before. The only things I want to discuss with you at the very bottom, there's some values for resistivity there. And I just want you to notice that all the metals there have 10 to the power minus 8, 10 to the power minus 7. Very, very small values, tiny values. Whereas glass at the bottom is 2 by 10 to the 11. So if you compare glass and iron, that means glass has 2 billion times the resistivity of iron. Factor of 10 to the power of 18 difference. Okay, so very, very different in the resistivity of a metal and a conductor and an insulator of electricity. Okay, so what I wanted to bring to your attention is question 14, and I'll just go through the solution here um, for you now. Okay, so you can see everything there, hopefully. We're doing question 14. And we know that the equation that allows us to work out what the resistance of a substance is, or of a length of wire is rho L over A. Rho is the resistivity, L is the length, A is the cross-sectional area, and R is the resistance. So a question asks about a copper wire. So we know from the table that the resistivity of copper, chemical symbol Cu, is 1.75 by 10 to the minus 8. And the unit for resistivity is ohm meter, 1.75 by 10 to the minus 8. The question asks you, what length of wire do you need? So we don't know what the length is. We're being asked to find that. And we're told that the resistance is 150 ohms. And I suppose the difficulty in all of this is working out the value for A. You're told in the question there's a diameter of 0.018 millimeters. Now, we tend to work out areas of, the cross section of a wire, which is a circle. So we tend to work those out in terms of a radius, pi r squared. So the diameter is that, so the radius is half of that, 0.009 millimeters. Of course, millimeters is not the unit we want to use for lengths. If we're working on the SI system, we need to change the milli. And the easiest way to do that is just to write it down as milli is the same as by 10 to the minus 3 meters. Okay, and A equals pi r squared, which is pi times 0.009 by 10 to the minus 3 all squared. So it's a very, very small number. You'll remember from the measurements we did on the Constantan wire that the cross-section area of that was very, very small. So I'll do the 0.009 exponent minus 3, square that, and then multiply by pi. And I get 2.545 by 10 to the minus 10 square meters. Okay, so that's our area. So we know everything now. We just want to get L. So one way of, probably the easiest way of doing this is to rearrange the equation before you put in the numbers, because the numbers are quite long. And the same principles of maths that we've been using all along apply to letters just as much as it does to numbers. So for example, I want to leave L on its own. So I want to shift that A across and I want to shift that row across. Do one thing at a time if you're not confident about this. And of course, to get rid of the A there, we multiply by A up here and they'll cancel out. So that if we multiply by A up there, we have to multiply this by A. So therefore, our first step would be R times A equals row L. Now I want to leave L there. I need to move the row. Divide by row on this side, they'll cancel out. So I divide by row on this side. So RA over row equals L. And so you put in 150 times 2.545 by 10 to the minus 10 divided by 1.75 by 10 to the minus 8. And from that we get 150 times and I get 2.18. And that is the answer given in the notes. Okay. So the only tricky part that really is in working out the cross-sectional area of the wire. Manipulating the formula, yeah, it may catch some of you out, but just be careful one step at a time and follow the rules that we've used all along in the module. Okay, so if we return to the notes, we'll just move on to a couple of topics. Open circuits and short circuits. I'm not going to spend a lot of time on this, but all I want you to be aware of is that an open circuit is where there's a current that's got, we need a full circuit for current to travel around. If there's a break in the circuit, that is called an open circuit. And a common break that we have in many circuits is just a switch. When you switch off something, you're breaking the circuit and not allowing current to flow. Okay, so we have a symbol for a switch. Oh, I've gone too far. So here's the symbol for a lamp, and there's a switch. So you can imagine if you press down on the switch, those 2 points meet, and current will then flow in the circuit, and the lamp will turn on. You flick the switch, that opens out, and the lamp will go off. Now, you may be wondering about potential and things like this. So if I just show you again on a diagram. So if we take that example of the open switch and the lamp. If we think about potential, say this is 5 volts. Well, obviously everywhere here along that simple wire is 5 volts. Everything here along that simple wire is 0 volts. But you might be wondering what's going on here. Well, remember, there is no current flowing in the circuit. If there's no current flowing in the circuit, then there's no potential difference across the lamp. V equals IR. There's no potential difference there. The lamp isn't generating or losing electrical energy in the circuit. So in fact, there's no potential difference. So all the way up to here, the potential at that point is 0 volts, and the potential at that point is 5 volts. Now, one of the implications of that is as you push the switch closer and closer to making contact, when they're very, very close, a voltage over a very narrow gap creates what's called a large electric field, and that can cause a spark. So you sometimes quite frequently get sparking whenever you flick a switch. I know if you've ever turned on a heater or a kettle in the dark, you might see a little flash when those two come close together. So you'll be advised if you ever smell gas leaking or suspect there's some flammable material in the air, don't switch on or off an electrical device, because when you open or close a switch, there's a strong chance of creating a spark. Okay, so that's an open switch, open circuit. Basically, a switch is the best example of that. A closed circuit, or a short circuit is a little bit different to that. And generally this can happen by mistake. I've done it before now, setting up circuits in the lab. And basically what happens is you connect a simple wire. You bypass the resistance in the circuit. Now that circuit, remember when you've though effectively current is coming down here, some's going that way, some's going around that way. And the resistance of this path is 0. And when you have two resistors in series in parallel, the resistance is lower than the lowest resistance in the circuit. So in fact, you've got this is now 0 resistance circuit. V equals IR. V over R equals I. If R is very, very, very small, then you get a huge current. Huge currents lead to heating, and this is a fire risk. Okay, so short circuits can be very, very serious. Okay, because of that effect. Right, so just so you know what the terms mean. Open circuit means there is a break in the circuit, but there's still voltage, and that can be dangerous, particularly if this is a high voltage. Short circuit is where you bypass a resistor, and that also is dangerous where there's a possibility of a fire. Now, the way that we need safety measures to protect us with these situations. So one such safety device is the fuse. And as it says there, fuse is an encapsulated fine piece of wire which conducts electricity. There are fuses in nearly every plug and socket that you have in the house. So a fuse has a fuse rating. So it could be a 13 amp fuse would be a typical one for a kettle. So a 13 amp fuse, which means that if the current goes above 13 amps, the fuse wire heats up and melts. And that breaks the circuit and stops current flowing. So you may be wondering, well, what's going on? Why 13 amps? Well, that basically means you use a fuse that is a higher current rating than the current you expect the kettle to draw. So we'll do some calculation examples later, and you'll see this in practice. Okay, so I won't say anything more about it now, but you'll see when we get to the calculations. Now, one thing I did idly pass by there was this idea that current going through a wire heats it up. So if I stop sharing there, so power, as we've seen in our in the mechanics section, power is energy divided by time. And when an electric current flows through a resistance, it loses energy. Okay. Remember the potential difference or potential? Potential difference is the energy lost per coulomb of charge flowing. Q is coulomb of charge flowing. So I'm just going to do a bit of witchcraft here with a few equations, but just see if you can follow it. The current is charge divided by time. So I can now work, I have an expression for Q. If I replace Q equals IT. So I can take this equation and say V equals E over IT. I move the I up to here, and I get VI equals E over T. But E over T is power. So the energy per second coming out of a resistor is simply the potential difference across the resistor multiplied by the current flowing through the resistor. So that's also called the power of the resistor. So P equals VI. Really important equation. Possibly. No, I was going to say the last equation new equation I'm going to give you. One more to give you yet, but P equals VI. Very, very important. Now, there are a number of ways of writing the same equation because you know V equals IR. So if I replace V with I times R, I get I or I, which is the same as I squared R. That's another equation for P. And if you look at I squared R, that's kind of like I squared R squared divided by R, which is V squared over R. So we have these three equations for power. But basically what I'll ask you to do is just stick to one equation for what we'll be doing in this semester. So power equals VI. Between that equation and V equals IR, you should be able to work out any calculation that involves power. So remember, electricity flowing through a wire or any resistance will tend to warm it up. The amount of heat that's generated is given by this expression. The power is the heat per second, remember, the heat per second, and the unit is watts. You take the voltage, the potential difference across the resistor, multiplied by the current flowing through the resistor. And if you look at the electricity question in those past papers that are available online, it asks you what's the power. It asks you to work out what's the potential difference across a resistor, what's the current flowing through the resistor, and then asking to work out the power. The last bit is very, very easy. Once you know V and once you know I, just multiply the two numbers together. That gives you the power in watts for that resistor. Okay. So share. So if we move to the bottom, so those are our equations. And then to settle you into using those equations, we have a set of problems here. And I would suggest that, well, maybe I'll do question 15 first, and you might have a look at one of the other questions then. That's uh, when I've done this one. Uh, okay, there's a few ones there, but okay, we'll look at question 15 first. They're quite quick questions. There are simple equations involved, so the questions shouldn't take too long to do. But I'll do question 15 first to show you the principles that this is all based on. Right. Sorry, I shouldn't have stopped sharing there. We should just, well, if you have the notes in front of you, we're looking at question 15. An electric kettle has an element with a power rating of 1.2 kilowatts. Domestic power supply voltage is 220 volts. What current flows in the element? Select a suitable fuse for the kettle. What is the resistance of the element? Okay, so stop sharing. So first of all, as always, with questions like this, we're on question 15. Extract the information that you want to use or that you're given in the question. So there's a power rating. First thing we're told, power rating is 1.2 kilowatts, which is 1,200 watts. Remember, kilo means 1,000. Oh, take that down. The domestic power supply is 220 volts. And part one asks you, what's the current? As always, question mark, do we know an equation that relates these three things together? You bet your, whatever the phrase is. P equals VI. So we apply that 1200 equals 220I. To get I on its own, you divide by 220, divide by 220. That's I. And work that out. 1200 divided by 220 equals 5.454545. So we'll just say 5.45 amps. That's a chunky current. That's much, much bigger current than anything we've seen before. Heaters, particularly heaters delivering high power, tend to use very large currents. Okay. Now part two asks you about the fuse. Select a suitable fuse for the kettle. So what this number up here tells us is that if the kettle is working correctly, then it will draw 5.45 amps of current through it. So that means there's no point in selecting a fuse that is lower than 5.45 amps. If you have a fuse that's 5 amps, if you turn on that kettle, 5.45 amps flows and the fuse will melt because a 5 amp fuse will melt because the current is greater than the rating of the fuse. So we need a current greater than 5 amps. We need a fuse with a rating greater than 5.45 amps. And so the next highest one up is 13 amps. You just choose the next current rating upwards. Okay, part 3, what is the resistance of the element? Well, V equals IR. 220 equals 5.45 times R. Again, divide by 5.45 divided by 5.45. 220 divided by 5.45 equals R equals. Now, I've left the number in my calculator, so I'll get the exactly correct answer. You may get it. If you're rounding off, you mightn't get exactly this. But what I get is 40.33. It's a resistance, so it must be in ohms. Okay. So I'm gonna carry on and do the other questions, but if you want to pause and attempt each question as we go along, by all means do. They're quite short to do. So, okay. So just carrying on. Question 16. In a car, there's a 40-watt headlamp. That's a power. Anything with watts in it is a power. Using a 12-volt battery. So the voltage is 12 volts. Determine the current flowing and hence work out the resistance. I equals, so P equals VI. 40 equals 12I. Divide by 12, divide by 12. 40 over 12 equals I, which equals 3 1/3. 3.33 amps. Okay. And then the second part is what's the resistance? Well, again, V equals IR. 12 equals 3.33 times R. 12 over 3.33 equals R. And that equals 3.6 ohms. Okay. That's question 16. Two more, as I said, they're very short questions. Again, if you want to stop and work it out for yourself, by all means do. Question 17. What is the maximum safe current that can be passed through a 10 kilo ohm resistor with a maximum power rating of 0.25 watts? Okay, so we have a power of 0.25 watts. Very small power. Okay, the power in a lot of resist. Anything you do, by the way, in a lab class will be very, very small power ratings. Or equals 10 kilo ohms. Remember, you have to work in SI units, so the kilo has to be replaced. So it's 10,000 ohms. And you want to know what I is. Well, actually, this is a case where we're going to have to use one of the other equations for power. Okay, you won't be given a question like this in a test. We'll stick to problems you can solve with this with P equals VI and V equals IR. So we have I, R, and P. The equation that links those two together is P equals I squared R. So 0.25 equals I squared times 10,000. 0.25 over 10,000 equals I squared equals, just to get this right, 2.5 by 10 to the minus 5. Oh, I think we're going to get 5 by 10 to the minus 3 when we square root it. So just square root that. Yeah. So I equals 5 by 10 to the minus 3 amps. And 10 to the minus 3 amps is 5 milliamps. Moving quickly along. Question 18. How much heat energy is supplied in 1 minute by a heating element which passes a current of 5 amps when there's a PD of 22 volts across it? So I is 5 amps. The potential difference is 22 volts. And you're asked for the heat energy supplied in 1 minute. Okay, so we want to work, the best way to do this, work out the power first, which is the energy per second, and then multiply by the time. So the power is, we're trying to find that. So P equals VI, which equals 22 times 5, which is 110 watts. Now, we're told that the power is 110 watts. We've worked that out. The time is 1 minute, 60 seconds. And what's the energy? Sorry, energy equals. So remember, power is energy over time. Multiply by T there, multiply by T here. So power by time equals energy. And that equals 110 by 60. You get 6,600 joules. So remember that this is a question about energy, not power. So joules. Right. So that's the heat that is emitted in 1 minute when you've got a 110 watt heater or 110 watt power resistor. Okay. I just want to cover one last little bit. If we go back to the notes. When we finish those questions, the heating effect of a current. And this is something I've thought about down through the years. But what I'm showing, you have in your kitchen, you may have a toaster and it's plugged into the wall. And the current passes along the wire in the lead, and then passes into the very fine wire in the resistor, in the toaster. Now, why is it that the toaster wire gets very, very hot, and yet the wire in the cable doesn't? Well, really, the toaster wire is very, very fine. And so it is a very, very high resistance. Whereas the conducting wire is a much thicker wire. When I say the conducting wire, I mean the wire in the cabling. It's much thicker wire. It is a much lower resistance. And if you could attach a small resistance to a large resistance, then an awful lot of the potential difference gets dropped across the large resistance. So all the power, P equals VI, it's the same current for both, but the vast majority of the voltage is across the element wire, the heated part, and it gets hot. The conducting wire is much lower resistance and stays at room temperature. Okay, we'll talk in the next section about potential divider, and that will kind of explain why this difference between the thicker wire and the finer wire, and why the finer wire has all the voltage rather than the thicker wire. So I think that's a good point to stop for today. I'm just going to stop here and stop recording. So I'll have another video up in the next day or two. I think there may be, it'll either be 2 more videos, or possibly 3. 3 short ones, 2 longer ones. Okay, and then we'll be finished. So all the very best.